Good evening, everyone. Thanks for coming out. Looks like we have a great crowd for the presentation tonight. A lot of names I recognize too, so good to see everyone tonight. And glad everyone could virtually join us for our Zoom session here for the ARES Academy 2020. And our topic tonight is station and repeater hardening. With special attention to some ARES topics here. So just some housekeeping things before we get started. I'm sure a lot of people are familiar with these already, having been through to some of our other sessions so far this month, but just some basics on how we're going to do the webinar. Everyone's in kind of a view only mode, so we're going to use the Q&A button to ask questions, and then we'll get to those after the presentation, just so we make sure we have enough time to cover all the content for everyone in the 1 hour block. And then I'm more than happy to stick around for questions afterwards. You know, this being virtual, it's kind of hard to get that feedback. So I appreciate any questions people have, and like I said, I'll spend as much time as we need kind of going through those afterwards. So to set the stage here, this slide kind of shows how I was thinking about the topic when I came up with the presentation we're going to run through tonight. So as emergency service communicators, as ARES operators, you know, what is our goal? And our goal is communication resiliency. So that means we keep the messages flowing, we keep, you know, information moving through our networks from the points, you know, point A to point B, getting everything where it has to go. And we're talking about station hardening tonight, and we're talking about some kind of technical things that you can do to your station, to a temporary station, to a repeater station, whatever link in that communication system you're charged with, making that more resilient through some technical hardening. But that's really only one piece of it, and it should complement the resourcefulness of you as an operator. So some of these things are going to contribute to that resiliency, but a lot of it is also going to be made up by your resourcefulness and your ability to adapt to your situation and to kind of overcome obstacles that way. So I just want everyone to keep that in mind as we're talking about topics tonight, that this is one piece that's going to complement you as an operator and your skills as a ham radio operator to keep the communications going and support our ARES mission. So under station hardening, there's a breadth of topics, and really to make this effective and to stick with the time that we're allotted here, we've got to focus, right? I mean, because there's tons of things. This could be, you know, this could be an entire month dedicated to station hardening. So I picked two topics. One, because they're pretty basic, right? Basic meaning they're applicable to a lot of different types of ham radio stations. They're applicable to a lot of different types of ARES missions. And that's backup power, which is a huge one for us in MCOM, right? I think this is one that people may know a lot about, and there also may be some new things people can kind of pick up, and that's obviously the goal for tonight. The other one is surge suppression and protecting your station from surge events and transient voltage. So those are the two we're going to kind of zero in on tonight. Just to, again, as a matter to limit this and to make sure we can communicate some effective information within this 1 hour block. So we're going to jump right into to backup power and to the topic of, you know, hardening your station from the perspective of power loss. before we consider, solutions to backup power, we obviously have to kind of form the scope and what do we need to power, and what does that look like from an equipment standpoint? Because determining that is really going to let you have a more effective solution. So the first topic, we look at this, what radios. If you're talking about a home station, we've all got tons and tons of radios. Which ones do you actually need to keep going in order to fulfill your ARES mission? What power level? This is applicable to, both that home station environment and a repeater station environment. With repeaters, when we're on main power, we might have the luxury of a higher power level. Once we go to backup, if we understand the limitations of reducing that power, it can give us a big advantage when we go to backup power. Same for your home station. Understanding, if I limit the power level, what is the effectiveness of my station at a lower power level if I need to go to that for backup electrical power? And that's, of course, where drills, communications exercises, things like that come into play, because that's really where you understand, okay, what power level do I actually need to be effective in this role? Or, if that's a typical role you have in the ARES organization, or understanding, hey, I'm on backup power, I can't be the simplex net control, or I can't be the a relay station on simplex because I need to reduce my power for power level on the radio for backup, but I can hit this repeater if it's on the air, or I can communicate with this group of operators locally. So I think that's something to keep in mind, right, when we go to backup power, because we can think, okay, this is how much my radio needs, but if we push the envelope a little bit, what can we actually get away with? And is that going to contribute to a backup power solution? Computers and networking. I mean, we've had topics about narrowband emergency messaging, of course, so far during this, the ARES Academy. Computers are becoming more and more a part of the ham station, of the EOC station. What are the implications for that? Same thing, what do we need? What can we shed going to backup power? Networking equipment, that all the peripherals that go along with your computer, digital modes, anything that you need to operate your station effectively. And it's a really basic point, so I hate to say it, but it just sets the table, right? And we have to think about this scope because the cost is higher the more power you need. And that's not only monetary cost in equipment, but that's also the space we're going to need and the amount of extra equipment to keep your station on the air if that power is much higher. So another part of that scope is, how long do we need backup power? And I'm sure a lot of people are bristling at this slide right now, right? Because this is ARES. This is when all else fails. As we got, it's forever, right? Oh, we gotta have backup power forever. If we think about it critically, though, we can really kind of hone in our solution, right? Because it's mission specific. When you think about where, what your role is in ARES, if my role is, I'm, all I do, my main role is, say, a radio operator at an EOC or at a hospital. My home station, I only need the ability to monitor the net until I know that EOC is activated, and then that's where I shift my focus. The amount of power I need at my home station is not as great, right? Because I'm not going to be expected to keep that station on the air throughout a prolonged incident. The reliability of utility and the accessibility, that's especially repeater sites is what that speaks to, right? I mean, if we've got a site that's remote and we know it's going to be a long time before we're able to get emergency generator in there or restore power, then we definitely have to look a lot more critically at a long-term power solution. If it's something that we know we can get in within a day or so, then we can scale back that solution. And same as before, again, that longer term power, that longer term solution is definitely going to have more of an impact in equipment. So understanding what the limitations are, what the requirements are for your length of backup power is again going to help us refine that solution. So with the runtime especially in mind, we can think about our various solutions for backup power. And we're going to go into detail on each one of these to kind of run through some basics of what they are, how to think about them, and how to, how to specify them for your need. So we have uninterruptible power supply, UPS, as our first one. That's our short-term solution. It's quick, but that is not a long-term power solution. We'll talk about why, and we'll talk about where that is most effectively used in the following slides. Backup battery is kind of our middle ground. It's such a wide open topic that it can be a short term, it can be a long term. It's really flexible based on how you implement it. And then of course we have generator power. Backup generators are kind of our brawn of backup power. They're definitely a long-term solution, but they also have some limitations, especially in the very short term. You can see that arrow is offset a little bit, and that's intentional because we're going to talk about generators are not your instantaneous power source. They take a little support to get up and running, but then they can provide you the most power and the highest amount of power for a prolonged incident. So when we talk about an uninterruptible power supply, everyone calls them UPS because, as you can, tell by me saying it, it's, a little bit of a mouthful. So what these devices are, and these are extremely common across a lot of different industries, is they provide very quick recovery, as the name suggests, to AC power loss, to the point where AC powered devices will not notice a loss of power. And that is really the main goal of these devices. That's what they're designed to do, and that's what you pay for. The way they work on a very basic level is they have an AC input. It converts it to DC for power storage. And then when that AC input is lost and you need backup power, it automatically switches to the DC batteries, converts it back to AC, and provides that power to your devices. And so again, it's very quick recovery. So this is aimed at equipment that is, one, critical to stay operational, and that any loss of power to that device, any restart or reboot of that device is extremely disruptive. So obviously where this gets used most is in computers, networking, the IT world, where those servers have to stay up, and if they go down, you have a intolerable amount of downtime, or there's some sort of user intervention that's required to restart or to get systems back up and running. So if we look at this from an ARES perspective, right, a UPS, not necessarily an effective backup power solution, or I guess I should say a necessary backup power solution for something like a radio. Our radios boot pretty quickly. Generally speaking, there's no detriment to them. You know, if they were to lose power for 30 seconds or something like that, we can get those back up and running fairly quickly. But if we think of something like a repeater, excuse me, especially one that may have a microcontroller or something that could take several minutes to boot and is primarily an AC device, that is definitely more of a candidate for a UPS, because you're preventing that reboot from happening. And that's what a UPS can do, is it prevents that device from ever seeing any power loss. A term you'll hear a lot when talking about UPS is they carry the load. So what that means is they're not a long-term power solution. They're designed to carry your AC power until something long-term can kick in. Now, that doesn't mean that there aren't long-term UPSs. There are. They're just very large and very expensive, and I would say more on the atypical side. Usually your UPS is a transitionary backup power source that brings you, that it absorbs anything that's, say, momentary, you know, any quick power losses, any kind of blips in your utility power, up through several minutes to several hours, depending on the load and the size of your UPS. But if you're getting into days of power outage, it's hard to rely on a UPS, again, unless you have a very large solution. Our cost drivers for UPS, primarily it's load size. The more power you need from this UPS, the more it's going to cost, just because you're going to need more and more expensive electronics. And then once you're in that load size, the amount of runtime you need is going to scale that cost up and down as well. Once you have a load size, you're essentially paying for batteries. So it doesn't increase as much if you're at the same power level, but it still will increase your power, your cost, if you say, okay, I need a UPS that's going to run 30 minutes versus 4 hours. When we get into types of the three main types of UPSs, because you can see, okay, what's the difference between, you're talking about these are really expensive ones, but then I can go into Staples and buy a computer UPS. So, what's the difference? So your most basic UPS, this is what you see in consumer products mostly, is what's called an offline or standby UPS. And that is essentially a battery backup, if we think about it. It's got an AC charging circuit, charges that battery inside the unit. And when it senses input power loss, it switches over to the battery and obviously converts back to AC. For most devices, this is fine, because even though it's a relatively slow switch as far as a UPS is concerned, it's fast enough for most computer power supplies. There's enough capacitance in there that they're not going to see that hit. But in extremely critical environments, very sensitive electronics, obviously that wouldn't be acceptable, and that's where your other more complex power supplies come in. Your online power supply, as the name implies, and contrasted with the offline power supply, it performs what's called double conversion, meaning all of the output power that's coming from that UPS is actually coming off of the battery and is converted to AC. So your input comes in, is used only to charge the battery, and then your entire load is running off that battery all the time. So it gives you very high power quality and a zero recovery time from input power loss, because you're always on the battery, you're always pulling off those batteries. your devices never see power loss. They never see mains power. And highest cost with these, obviously. A kind of middle point between these, compromise that takes some of the best of the full online version and makes it a bit more cost effective, is Line Interactive. And that is just really always sensing the AC input and has that battery there to condition the voltage coming in and to give you a clean and constant output at all times, no matter what AC is coming into the device. That battery is there to boost it up. So it gives you slightly faster recovery time than offline, but really the main advantage of that is the power quality you're going to get out of it. So that's just some information on understanding, right? If you go to look at UPS, to source a UPS for your application, what do some of these different terms mean? So if we think about that UPS, like I said, it's mainly focused on AC loads, right? That's what they're optimized for. That's what you're paying for in a lot of that cost, and a lot of the technology in there is made for keeping AC devices online all the time. But when we think about amateur radio, when we think about the equipment we use, at the end of the day, a lot of it's not running AC. We don't need that AC power. Our radios, our biggest drain, our biggest load in the shack is DC. It's at 13.8 volt DC. So a lot of that, the pieces of the UPS are extraneous to what we need. And we can use backup batteries more effectively, more efficiently, because we don't need that AC component. And you can use, your battery charging, battery switching devices in different configurations to mimic that same functionality that you get out of a UPS. So we can have a battery, we can have a manual switch over, right? We can have that kind of offline model where we charge our batteries, have them sitting in a bank ready to go, but we also have our power supply that's on mains power. We lose mains power, manually flip a switch. There are automatic switching devices in order to build that offline functionality. Online, we can build as well with a battery bank, using your power supply, your DC supply to constantly charge those batteries. Have your load, your radio in parallel with the battery bank, and it's always drawing off the top. Never going to notice a fluctuation in power. And of course, there are power supplies that even themselves integrate an automatic switchover and charging to batteries. So there's a lot of options with batteries that you as the operator can take control of and build exactly what you need based on your scenario and based on the kind of backup power you need. But with that obviously comes the responsibility for charging, maintaining the batteries. That automatically was done in that UPS. Now, if you've just wired up a battery bank for yourself to use, that's on you to make sure it's effectively wired for charging and for maintenance of those batteries so it can be ready when you need it. And as a cost comparison to a UPS, you can get a lot more effective runtime, higher load if you're going direct to battery, because you're eliminating that conversion. You're eliminating a lot of the sensors and technology that was needed to give you reliable AC support, simply because we can operate at that DC level. I'm not going to get too much into battery chemistry, again, because it's kind of a topic in and of itself. The traditional type of battery that we've used for years and is the most cost effective and is kind of simplistic in charging, which are the two main advantages of a lead acid style battery. Within lead acid, there's a lot of different style innovation in that design. They also have implications as far as battery maintenance and environmental constraints, temperature range, things like that. But generally speaking, they are lower cost and they're simpler to charge. So when we talk about, building up our battery bank and the devices we use to charge that and recharge that, a lot more options, a lot lower cost if we're using a lead acid, more traditional style battery. When we talk about lithium batteries, mostly for our applications, we're talking about lithium iron phosphate. For a high power storage battery, that's really kind of where the best payoff is with the lithium technology. These have major advantages over lead acid batteries in energy density, kind of leading the way with those. Meaning you can get a lot more power out of a smaller, lighter battery, which again may or may not be an advantage depending on your application. Something that is fixed, while you may have smaller footprint may be an advantage, the lighter weight may not get you as much. But there are also some advantages in the service life, your ability to discharge them to a much lower voltage and to cycle them back up to full charge faster. Preparing this and looking at the differences, right, between lead acid and lithium ions, this was actually a very helpful site. And I wanted to just share some of their graphics because I think they offer a nice visual showing some of the advantages and disadvantages here. This is a battery company, so at the end of the day, they are trying to sell you batteries, but I think they did a good job in my reading of just looking at some of the advantages, disadvantages, trade-offs, and understanding what you're going to run into. If you're using one type of battery versus the other. I thought this chart was an interesting way to put it, and the charging profile, which shows, again, back to the first point regarding the charging technology, your lithium batteries, you do have to pay more attention to the charging technology you're using, and your options may be more limited there compared with some of the sealed lead acid batteries, which are a lot more robust when it comes to charging. You can really charge them with anything, and it's a lot easier battery to implement in a battery bank, but and that's really, I would say, the biggest advantage from a ham radio, from emergency operations standpoint, is you've got a battery that you can be a lot more resourceful with when it comes to charging it, and you're not going to have to worry as much about having the appropriate charger or having that available if you need to bring those batteries back up to voltage in order to continue operating. So some resources for people who want to kind of dig into this a little bit more when you take a look at the slides. When we build up backup, when we have a battery bank for our station, right, if we decide to go that direction, I would make the most of it and do as much at 12 volts DC as you can. right? Because as we saw with the UPS, that conversion, you know, is costly in power and in technology. So if you can stay at 12 volts for a lot of your devices, that's going to give you a really effective backup power solution. So we talked about computers being a big use case for UPSs before, but if you think about using just a laptop rather than a desktop computer, those operate at 12 at DC. I mean, eventually all computers operate at DC, but the input power to your laptop is at DC. It's often higher than 12 volts, but you can source a 12 volt designed power supply for a laptop very easily. And a lot of times it's doing a boost conversion up to say 18 or 20 volts. But that's a lot more efficient than sending, you know, taking your battery power, converting it to 120 volts AC, only for your laptop brick to convert it back down to say 20 or 18 volts DC. You know, you're going to have some inefficiency in the conversion up, and you're going to have some inefficiency back in that conversion down. So if you can keep things at 12 volts, keep them at DC, that's going to be a more efficient backup solution. Of course, the downside is you're at DC, right? So your copper loss is a lot higher. So you got to make sure you're keeping your conductors short and oversize them for voltage drop if they are a little bit longer. But just something to keep in mind, if you backup power solution is DC, make sure you're doing as much as you can at DC in order to make the most of it. Generators, again, I think this is something people are pretty familiar with. You know, a lot of us have these in our homes just for normal power loss. And when we think about the spectrum of backup power, as we were talking about, as we showed in that first slide, this is generally considered your long-term solution. Obviously, fueling and things like that are considerations for keeping this viable long-term. But this is going to give you the highest amount of power, and it's going to let it run the longest compared to the other two we discussed. And it's really kind of to be used as a complement with those other solutions, right? Especially the UPS. The UPS really is going to need to be followed up by a generator in order to be a long-term solution. Our two main categories, portable generator, fixed generator. Biggest trade-off being, you know, the ease of use or the, you know, the quick recovery with a fixed generator versus the flexibility of a portable generator. What you're paying for in these is your load size. You know, the bigger, the more power you need, then the more you're going to pay for a generator. Other than that, you're going to pay a little bit more for efficiency, noise reduction, especially in fixed generators, is going to be another cost driver with those. This is a solution that I don't think gets talked about as much as a kind of middle ground between your portable and fixed generator, in that it gives you the flexibility to use a portable generator if you need it, but it also doesn't, you know, it'll also allows you to have that portable generator if you want to take it somewhere else. And that's a gen plug. And so this is a hardwired inlet that wires directly into the distribution panel. So this is something that's installed by an electrician, and that is integrated with, you know, the mains power. And so it allows you to have kind of the functionality of that fixed generator, but you still have the portable generator that you can bring somewhere else if you don't need backup power at that location at the moment. This is also a way to back up a fixed generator. And I've seen that in some critical locations where they'll have a fixed generator that'll be ready to go, automatic switchover, but they understand that that is not 100% foolproof, so they have a gen plug as well, so that a temporary generator, portable generator, can be brought in the case you have a malfunction with your fixed generator. This is a, this is a good solution, in my opinion, also for a repeater site, where you can have backup batteries to provide medium-term backup power for a longer duration event. Bring in a portable generator to get that back up on the air. So a transfer switch is an important part of a fixed or gen plug installation. And what this does is it keeps your generator isolated from the utility. And that's an important thing to have for safety of the electric utility workers, because without this, there's the ability to backfeed from your generator onto the electrical grid. And that can be deadly for the electrical workers when electricity essentially shows up where they're not expecting it. So there are two types of transfer switches: automatic, which is designed to work with a fixed generator, and manual, which is designed to work with a gen plug. The manual is essentially a series of interlocked circuit breakers, and you have to go in, you switch from mains to generator, and it does that disconnect on the utility side and connects in on the generator side. And then when your electrical power comes back up, when your utility comes back up, you switch it back. An ATS just does that automatically. And it's designed, as part of a fixed generator solution where it senses loss of utility. It starts up that generator. When that generator has come up to its running voltage, then it brings the load on there. An ATS switches quickly, it switches automatically, but it's not instant. And that's where UPSs come in most, and where I see UPSs the most is they've got a generator, they've got an ATS, they know that's going to come on in, say, 30 seconds. But within that 30 seconds, all of your AC devices, have lost power. They've shut down. And you can't rely on this to keep constant power. So that's where a UPS, possibly a backup battery solution, comes into play, because it can bridge the gap, carry the load from power loss to generator start. It also doesn't hurt if you're relying on a backup generator to keep that UPS runtime longer than typical switchover, just to prevent any issues with automatic startup, right? Generator doesn't turn over, in a couple of minutes, you've got to go start it manually. You want to build in some buffer on your UPS side. This is a slide that I actually shamelessly pulled right out of Dave's version of this presentation. I see Dave's on, so I appreciate you sharing those with me before. And I saw this concept, and I actually wanted to put this in because I like this concept, and this is the first I had seen it, and it just makes a lot of sense. So this is a simplified version of a generator plug where you don't involve your main distribution panel at all. And that makes it a much simpler and safer solution that anyone can implement. You don't have to worry about working inside your panel. And what you're essentially building here is you're building an extension cord into your house or into this building. You have a weatherproof inlet on the outside. You run some conduit, some Romex, and you have some outlets on the inside. Now, unless there's a generator plugged in, those outlets aren't doing anything. But if you lose power, you say, okay, you bring your portable generator there, you plug it in, and you have power at those outlets. You're relying on the circuit breaker inside your portable generator, so you don't have to do anything for circuit breakers inside the house. You just have to make sure, of course, that all the components you use to build this little generator circuit are rated for the output that that the circuit breaker in your generator is protecting. But other than that, I like this because it is a pretty simple solution that anyone can implement, and it makes it a lot safer to run your generator in a pinch, and really avoids the temptation of running the generator, in the garage or something like that, which we all know it can be a dangerous scenario. So thank you again, Dave, for this slide, and I just wanted to, make sure everyone saw that, because I like that solution, as a simple approach to applying generator power. So unfortunately, I am running a little bit long, which for anyone who's done a presentation with me before is not surprising, but so we're at the halfway point, switching over to our other topic, away from backup power to surge protection now, our other station hardening topic for tonight. I see some questions coming in. I'm going to try to make sure we get through all the content here, and then I'll answer those questions after. So I appreciate everyone kind of sticking with me through this. So when we talk about electrical surge hazards, we're talking about issues caused by lightning. That's what we're talking about here. And this is a dangerous situation. It's a concern for us as people who, operate ham radio, because this presents both a hazard to equipment, electrical equipment, and it can pose a hazard to operators as well. So what are we dealing with here in electrical surge? We're dealing with a high voltage situation. So that means in a surge, you're going to have electrical currents flowing in places that they don't normally flow. Things that are usually preventing electricity from flowing between 2 points. We're dealing with lightning, when we're dealing with a voltage that high, they don't do that job of holding off voltage. And of course, the currents we're dealing with are extremely high. So your conductors that normally conduct electricity fine, we get to these current levels, it's much too high for them to handle. And that's where we see, fire and burns, because just from that high current. So the combination of those is obviously a very dangerous scenario, because we have a lot more electricity than we're used to flowing in places that we're not used to having electricity flow. So our basic strategy for dealing with electrical surges is to isolate them and then give them a path to ground, right? So when we talk about our undesired paths, we want to keep that surge, we want to keep the lightning number one, we want to keep it outside, and we're going to talk about the ways we do that essentially in this entire section. And we want to, and we also, cut it off and also give it a preferred route, give it a route that we design to ground rather than letting it take, whichever one it is, which is going to, cause damage to equipment and prevent, off, also pose a hazard to us as the people, in with this equipment. So the way we isolated was a surge protection device. We're going to go through in detail some different types of SPDs, and those cut off those undesired paths. Some of those undesired paths are coaxial cable, electrical lines, things that are conductors, but in this case, we don't want them conducting. We don't want them bringing that surge towards our equipment and towards us. And then the way we give it a better path or a preferred path or designed path to ground is through grounding and bonding. There's a host of materials that go over surge protection, grounding. These are a list of some very good ones. National Weather Service Manual on lightning protection. Those are the guidelines, or not guidelines, the requirements for all of their facilities. Obviously, an organization that's pretty sensitive to lightning. So these are the requirements for grounding at all of their facilities. And it also gives us some good examples to use in our own surge protection practices. IEEE standard 142, and that is their document all about grounding. It's focused on industrial and commercial power systems, the power grid, but it is referenced in every document talking about communication systems as well. Kind of lays the groundwork for effective grounding. Article 205 of the National Electric Code talks about grounding and bonding, same thing as the IEEE document does. IEEE document is obviously a lot more of the science behind these effective solutions. NEC tells a licensed electrician exactly how they have to do it. And that is, that is the requirement for grounding, but it provides a lot of insight for those of us who are setting up our own station and, may not be working to that code, but it gives you the groundwork for that. And this last resource is the one, obviously, that I'm most familiar with, but it builds on really all of these, and it's Motorola's R56 manual, which contains a whole breadth of topics regarding building out a communication site, but it has an entire section on grounding and surge protection. And the same thing, it builds on NEC, on IEEE, it builds on all these codes and standards in order to have as that pyramid states, a de facto guideline, right? So a above and beyond best practice specific to communications, wireless communications sites. Those are all very long technical manuals that I think are definitely worth the read. You get a lot out of them, but they're not, they're not, there's no bullet points, right? You got to really dig into them. So some of the bullet points that you might get out of going through all of them is the importance of a low impedance grounding system. This provides the best protection, and it's constantly repeated in all of those documents. They talk about, it must be a low impedance grounding system. And so how do you get that? You get that by grounding with heavy gauge conductors. The smallest gauge wire that's mentioned in relation to grounding in R56 is number 6. That's the minimum that you can use and be compliant with that standard. And then as you get longer runs of ground cable, NEC 205 dictates, that you've got to get, coarser and coarser, larger and larger with that cable. So when we're talking about grounding, we're talking about heavy conductors. Short and direct grounding conductors, making them as short as possible and making them as direct as possible, straight line, rather than kind of cable routing that we might be used to with other cables. You want that to be as short and direct to your grounding bus bar as possible. A term you see a lot when it talks about connections are irreversible. So when you're talking about lugs for grounding, C-taps for joining two conductors together, something they emphasize is mechanically, those have to be irreversible. Anything that's got like a bolt or a screw that can be loosened is not acceptable in those standards, simply because, over time that will loosen, especially it's outside on a tower, vibration in the wind. Over time, those will loosen. So for them to, audit and certify a site to these standards, they want to see something that mechanically, it's completed once and it's not coming apart. The other piece is purpose designed hardware. And well, if we're not going to be audited on these standards, or we're not going to hyper focus on meeting the letter of the standard, a UL stamp may not get us anything. But it's the idea that use things as they're intentioned, especially when it comes to devices that are making these ground connections. You want something that is designed to conduct electricity. It's designed to conduct a lot of electricity. If it's going to be outside, it's designed to be outside in the element. Or if precautions have to be taken in the installation, if certain steps have to be followed, that those are followed. So what's our strategy outside? Our strategy outside is essentially bonding anything that's metallic to ground. So everything that that's related to our antenna support structure, towers, masts, antennas themselves at the appropriate locations should be bonded using some of those practices we talked about in the first slide to a single low impedance ground system. The best we can get here is a ring that covers the entire area of that tower, of that communications facility. So outside, the biggest thing is bonding everything using the appropriate hardware that's designed for, outdoor electrical grounding. And what that does is it directs the surge right down, and it's going to give, most of that current is going to take that low impedance grounding system going right into the ground. That's the part we talked about before, right? Isolate and ground. This is the ground piece outside, giving it that good path to a low impedance ground system. Another important piece of outdoor grounding is COAX ground kits. And what this is, you can see in these photos, is it's a sleeve that fits around the outer conductor of the coax and is used to ground that to your ground, or to bond it to your grounding system, excuse me. This is the best practice. Again, it keeps that surge energy. It keeps the most of that surge energy outside. It keeps it from, normally it's flowing in that cable. That cable's going inside eventually. With these ground kits, it's, you know, nice low impedance to ground, going to keep most of that current flowing outside. As you can see in the photo that kind of shows from the installation manual there, to install this, you have to cut the jacket off the cable. It's scary because if you do this the wrong way, yes, you will damage the cable. You will cause an SWR spike. So for that reason, these are coax specific. They are most common for hardline because of just industry demand, but you can find them for braided cable. Manufacturers of braided cable make, you know, their own version, and there's also third-party versions that are designed specifically for braided cable, like LMR 400 and cable like that. And then when you do this, when you install one of these, read the installation manual, you know, 3 times before you start. It's just something you definitely want to get right. And they, as you can see, the kits usually pretty much always come as shown above with essentially everything you need. Weatherproofing mastic and tape being some of the most important pieces there, because once you install this on the cable, you've got to make sure you weatherproof it securely, because you're opening up the cable. And if you don't completely weatherproof it, moisture is going to get in there and it's going to cause SWR issues. I included the link here to a YouTube video that actually was put together by Times Microwave for their ground kits for LMR 400. And I thought it was very good. It goes step by step, shows you installing this ground kit, how they do it, you know, the manufacturer recommendations there. So I thought that was a very good resource to you know, shows some best practices for putting these on. And it was something that I used because, you know, obviously this is a daunting task, cutting into your cable and, you know, slapping a you know, aluminum strap around it is not something that we normally think about doing in a coaxial cable. So having that resource was good for just kind of walking through it step by step. So once we come inside with our surge protection, you know, what's our strategy in there? So when we talk about our SPDs earlier, those are our isolation devices. Those disconnect and try to cut off those undesired paths for the surge. We want to install those as soon as your cable comes inside. So as early as you can. The standards have various lengths that they state, but essentially as soon as practical that's inside, you want to surge protect it. And then after the surge protection, you either want to ground everything and ground it again back to a low impedance ground system with large conductors, or alternatively, if you can, disconnect, right? So in a home station, it may be easier to, you know, right after that surge protector comes in, if, you know, you're not going to be using your station, or it's a lightning event, right? It's a high risk for a surge, is disconnected, because that you know, goes to our mantra there of isolating your equipment from the surge. You know, you still, everything's grounded at the surge protector there, but you take the you take the equipment out of the, out of the equation essentially. Why you need to ground, even if you have a surge protector, if you leave it disconnected, is something that we'll talk about here as we go into a little detail on coaxial surge protectors. So the basic way that these work is it uses a glass tube inside the SPD that shunts the center conductor to ground when a certain voltage threshold is reached. So essentially, the voltage gets too high, this switches so that center conductor in the cable is connected with ground. So that doesn't get you anything unless this is grounded really well and all of the devices attached to it downstream from it are also grounded really well, because you're, they're part of that parallel path for that surge, right? Even though, we want to take most of the current away at this surge protector right into our ground system, but there's still going to be some current that's flowing on the inner and outer conductors of that coax cable into your radio, into your repeater, into what's ever downstream. So that's why I said, if you keep this if you keep your equipment connected, you want to make sure that that's also well grounded, because there is going to be some surge current that's coming down from the surge protector, and you want to give that, a preferred path to ground, because if you don't, it is still going to find a path for ground for that remaining current, whether it's through control wiring, the wiring back through your power supply and AC, to your AC ground, which travels, through the walls of your house or building back to the panel, right? So, surge protector does a lot to prevent a surge flowing in directly on the center conductor, but there is still going to be some residual current downstream from this, and that's why it's important to make sure that you still have grounding on that equipment. This is not like it's not a substitute for a full kind of air gap from the equipment. So when you're picking a coaxial SPD, and this is obviously one shown here, this is what they look like. They're specified across a frequency range, power handling, and insertion loss, or so how much RF signal this will absorb in normal operation. So you just want to be aware when you're buying one that it fits your needs in those categories. It should be pretty clearly stated from the manufacturer what those are. The link I have here is to one of the manufacturers, Polyphaser, and some of their white papers, which go into a lot of technical detail on how these work. Again, it's a bit of a sales pitch, because they're going to try to tell you why the technology they employ in theirs is better, but it goes into a lot of the design behind them, why they work the way they do, and also, again, some best practices for implementing these in order to get the most protection out of them. We focus obviously on antennas and towers because those are what's sticking up in the air. Those are what, arguably are going to attract, a strike or a surge, But any metallic conductor can carry energy from a surge inside. And so we want to make sure that we are protecting on everything else that's coming in to our shack, into our building from outside. Some examples are listed here. Some SPDs for various types are shown. I got an Ethernet surge protection. This one on the bottom is a surge protector for a 75 ohm cable for an antenna, TV antenna, or for your cable service, your Comcast coming in. The grounding blocks that we see typically in like a cable installation, that's not a surge protector. It's not a substitute for a surge protector. You could think of that more as a ground kit. That's essentially what that's doing. It's grabbing the outside conductor there and grounding it, which is a good thing. Those help, but it's not a substitute for something that's going to protect the center conductor. And so looking at all the metallic conductors coming in as a potential source for surge current, you know, you kind of have two options, right? Surge protect them or remove them. And that's just a kind of good best practice, and something we look at a lot in the industry is like, if something's abandoned, it's not there anymore, you know, it's kind of a liability if that's a metallic conductor coming into your shelter. So removing stuff that isn't needed is definitely a best practice for surge protection. So the final topic when we're talking about surge protection for our discussion tonight is on the AC power side, because the AC power grid, being such an extensive network of metallic conductors, is a really big source of surge current coming in. And our typical protection devices there, right, that are meant to prevent fires and electrical shock aren't surge protectors. They're designed for another job. So AC surge protections, like our RF surge protectors, they have threshold voltage, and they shunt your electrical connections to ground when that's reached. An AC surge protection, just like RF surge protection, is most effective when it's as close to the input as possible, keeping it away from your devices by as much as possible. So the best method, obviously, surge protect it right at the panel, right when those mains come in. That, consequently is going to be your most expensive as well, because that device has to be built for the entire, if you've got 200 amp service, that's all of the devices in there have to, under normal circumstances, carry 200 amps. So that's more expensive, but again, provides you the best level of protection. When it comes to cost with these devices, no matter where they're located, the speed of the protection is also another cost driver. For more sensitive electronics or more expensive electronics, where higher or shorter clamping time is needed, you're going to pay more, because you're going to essentially have two devices in there that are doing that shunting. SADs, silicon avalanche diodes, and MOVs, which I forget the full spell, what MOV stands for, but those are the two devices that that provide the surge protection. Less expensive surge protectors will have one of those. More expensive will have both, and that's a kind of a big differentiator. As I mentioned, and as we saw in that previous picture, you've got hardwired SPDs, you've got soft-wired SPDs. Hardwires are designed to wire into your distribution panel, so they are installed by an electrician, but once they're installed, they protect all the circuits off that distribution panel. Best level of protection. A very good alternative to that is soft wired, and there's a wide range of them, and they're very easy to implement. This is good because in some situations you you can't specify, the electrical design. Repeaters come to mind big for this because, oftentimes, if you're lucky enough to get access to a site to put up a repeater, you can't tell them, hey, go install a surge protector on your panel. You're lucky enough that they're, might not be charging you for power, so you don't want to be too picky. But with these, whatever outlet's there, you can plug this in and provide a high level of protection. Oftentimes we see them integrated with power strips or power distribution, but they don't have to be. They vary in quality. It's pretty, there's a lot of different AC surge protectors out there, especially ones that are built into power strips, may not provide the best level of protection. Some do. It's just a kind of your mileage may vary thing. But that's why I wanted to show these devices on the bottom. These are something that I like, again, for repeaters a lot, because they're a single outlet surge protector, but I can plug any power strip off of that, and I know I have good AC surge protection because of this device. And then I'm not forced to, make sure I have a high-end power strip surge protector. I can just plug this in, plug everything else in downstream from that, and know it's protected. So I don't think those are as well known on the AC surge protection side, so I just wanted to bring those up. Single outlet AC surge protectors, because they can be a good solution. Again, easy to throw in your Go kit, easy to kind of bring anywhere, plug in, and you know that your equipment is protected without any other intervention. And that wraps up the presentation. I apologize for going over time on that. I hope I didn't have to rush through too much of the content, but that people got something out of this. Again, understand this is not a technical deep dive, so I hope some of the real kind of technically minded folks who know more than I do weren't disappointed by that. But what I hope it did give people is some strategies, right? Some ways to think about these hardening techniques, and something that they can maybe implement in their station. So I see we got some questions in here, and keep sending them in if you've got them and we'll take those as long as it needs. And if people have to drop off, I appreciate your attendance tonight. So Alex, I don't know if you want to sort through the questions, or if you want
absolutely.
me to have a look at them. Okay.
Sorted through a few here. The first one, going back to batteries and a little bit of how long we can expect a particularly rated battery to last. So here's the question. If you have a backup battery that says it's 75 amp hours, does that mean 75 amp hours at 13.8 volts, or what would you expect for a length of time a radio can operate?
So that's going to be battery specific. I definitely wouldn't expect it to be right at 13.8 volts. Usually, if you dig into the literature on the battery, they'll have a chart that goes through the discharge, charge and discharge voltage profile of that battery. It will be a nominal amount. You'd have, again, it's specific, but I would say it would be enough to power most radios over that amp hour life of the battery, but it certainly won't be up at 13.8 for the entire time.
All right, and then going back to our discussion that you had on generators and transfer switches. The question here, if you have a manual transfer switch, how do you monitor when the main power comes back on? And how do you handle that switch?
Some of them may have an indicator on them, but it's it's really, it's manual. So it's, you know, when the power company knocks on your door and says, hey, power's back on, or, you know, see your neighbor's lights come up. Again, specific to that component, it may have an indicator of some sort, but it is going to rely on you to go over and actually switch it, both on and off. So there's not necessarily a built-in way to know just looking at a manual transfer panel.
Okay, the next one is asking about grounding rods. Is there any benefit, or is it preferable to sync your own grounding rod to avoid HF resonance as opposed to using the grounding rod shared by your main power?
No, there's no preference to using a separate one. The best practice is actually to have all of your entire ground system be common. When it comes to grounding, the understanding, you know, outside of, you know, some perhaps specific phenomena, but, you know, that's grounded, that's your reference for everything else. So if you can effectively and at low impedance bring everything into the same ground network for a site or a facility, that is preferred.
All right, we have another one here asking about ground wire. Is there an impedance difference between 6-gauge solid versus stranded grounding wire?
There is slightly, not enough to make a major difference in that you need to use solid. Solid is better, especially in outdoor environments because of oxidation between the strands. So solid is preferred there, but indoors, stranded is perfectly acceptable and is used because of the flexibility, which allows you to get those straight and direct connections.
All right, we have another one here. I'm not certain if this is something that would be better to be referenced off of a data sheet for something like this, but Jeremy, if you know off the top of your head, typical DC to AC conversion efficiency for a UPS, and also perhaps versus a portable inverter. So that might be a little tricky.
Yeah,
but
I thought I'd
throw it out there anyway.
We got the trivia session tonight.
Oh,
no,
yes.
Good question, valid question, but it is going to vary. You know, one of those things like, you know, it's obvious I'm an engineer when I say it, right? But efficiency is one of the things you pay for, right? So, you know, a quick and dirty inverter, UPS, lower level of efficiency. Generally speaking, I'd say probably around, you know, I don't think we're in the case where stuff is below 50 or 60 anymore. I mean, switching electronics are generally efficient. You know, stuff's good. We're in the 70, you know, 70%, you know, up there. But, you know, 90% versus 95, that's, you know, that's your expensive UPSs, your expensive inverters, things like that. So definitely if you're looking to purchase one, a valid question to ask, a valid question to look into, but it is going to vary kind of across the market.
Okay, our next one here is a question on grounding for a shack. I have a second floor shack. Running a strap 20 feet to the ground, will that cause an issue with transmitting?
Excuse me. No, it should not. I mean, again, that's at ground potential. So it's, It shouldn't be, it's not going to radiate anything. I mean, we talk about HF, right? We talk about RF, taking all sorts of different paths, right? But it's going to sink. Whatever current's on there is going to get sunk to ground. So you shouldn't see any interference or change in operation, in a negative way, at least, from adding a ground conductor.
Okay, and then the next one here, are simple battery UPS devices like an APC also surge protectors? Again, this might be kind of model specific.
Generally speaking, UPSs are not, well, yeah, it is specific. They may be a kind of a basic level of surge protection, but I would not rely on a UPS to be a surge protector unless it's explicitly stated. And again, look, it may take some digging, but figure out, okay, what surge protection devices are used in this.
Absolutely. Okay, the next one. Could a nearby lightning strike induce enough voltage that would be sufficient to destroy microcircuits? If so, could this be mitigated somehow?
Absolutely. A lot of the times when we have damage from lightning, right, it's not a direct strike. I mean, that's obviously an extremely damaging event, but we can have events that can outright destroy equipment, or from an induced surge event. Oftentimes what you'll see is kind of strange and unexplainable behavior, or something just being finicky, a piece of electronics being finicky. And that's often the sign that, okay, it's not burned up. It wasn't a very high current device, but a strike, excuse me, or surge event, but there was enough to damage, especially things like, microprocessor silicon devices that are very sensitive. Mitigating that is same steps we talked about here, because it's going to be a high transitory voltage, even if it's not high enough to burn the stuff. It's higher than should be there, and it's what would be over the threshold voltage of a normal surge suppression device. So all the surge suppression we talked about, those practices, those prevent a wide range of events, from our more damaging direct surges to those caused by induced voltage.
Okay, we have one more here that I think is quite interesting. How long do these surge protection methods last in years? So, essentially, is there any shelf life or kind of date of expiration for any of these devices? That's a good thing to think about.
That's a very good question. So from the device standpoint, I guess I should say internally, these internal devices, no, they don't really have an expiration date on them. If there's a known surge event, it's absolutely a good practice to replace them, especially one that, is observed, or, did cause some damage or some noticeable effects. Replacing them after a major event like that, absolutely a best practice, even though some devices do claim to be multi-strike or be able to survive them. Still best practice replace after that. But without an event, for all of our interior or SPD devices and connections, not necessarily an expiration date on them. Anything outside is simply caused by the elements, and is going to be an issue over time. So I wouldn't say you have an unlimited shelf life or unlimited service life outside, simply because materials are going to break down. You know, use materials outside, obviously, that are designed for that environment. They're designed to withstand it. But even then, you know, you start getting above, 20, 25 years outside, obviously, depending on different environments, salt air, um, other harsh environments, are going to treat metals and are going to treat some plastics and things like that more. And what you don't want, right, is your metallic connections becoming oxidized to the point where they're no longer low impedance. Your nice, you know, copper crimped into tinned copper. Once that copper starts to oxidize in there, and even when you do weatherproof it, do all the best practices, it will eventually, your resistance to ground, your impedance is going to start creeping up. And once it gets, higher, it becomes less effective. So outside stuff, I would say every 10 to 15 years, you would definitely want to inspect it and test it. Visual inspections, as far as making sure, obviously, there's no cracks or leaks anywhere water's getting in. Nothing's, corroded or degraded in that way. And resistance testing for some of your ground components is a good practice. But I would say, you well installed, you should expect in the area of 20 to 30 years outside for effectiveness, but inspection on the order of 10 to 15 is a good idea too.
All right.
Answer to that one.
We have a question looking for clarification on location of SPDs.
Sure.
So, I know we touched on putting in a device as soon as the cable enters the building. This person's just looking for clarification. Would you still use, one of the cartridge SPDs on the cable exterior to the building?
You don't. It's not necessary to install one outside, and the reason is that's generally considered. Outside, you're susceptible to picking up a surge, right? So if you put it outside, you still have some cable on your way in that's supposedly on the protected side, but can still pick up a surge. So you definitely want an SPD on the inside. You can put one on the outside as well. But in that case, you would want both. And you can put both on. It's not going to cause any harm. And you can actually use an SPD outside, kind of like you would a ground kit. And that's a good way that, to avoid, some of possibly the pitfalls of improperly installing a ground kit outside, is you can put a surge protector outside, another one inside, understanding that that one outside is going to take most of it. That's going to provide you most protection, but you still want the one inside in case anything's picked up right before it enters the structure. Also, if you have a surge protector outside, make sure those connections are weatherproofed, and make sure it's either rated, the device itself is rated to be outside, or it's in a weatherproofed enclosure. I would say that's probably the biggest reason. We do see some SPDs outside commercially, especially on the cell side, because they have a lot of outdoor cabinets and outdoor enclosures. But I'd say the biggest reason that those are not, that there's not one on the outside is that extra step of weatherproofing it. And protecting those the coax connections on there from water intrusion, versus putting on a ground kit, which is going to, again, keep most of it outside. And then, you know, any residual, especially anything on the center conductor, is picked up on the SPD right as it comes in.
All right, so I think we're winding down, but maybe one more question here if you're if you're up to it, and maybe also a segue
absolutely.
into a future presentation. But aside from the topics covered tonight, you know, backup power and surge suppression, what are some other examples of station and repeater hardening?
So the biggest one that I know Dave does in his presentation, but I didn't want to, you know, take some time on, because again, it's kind of a presentation in and of itself, is kind of mechanical hardening for your antennas, for your towers, right? And designing those in a way, and best practices for making sure that your antennas stay up in adverse weather conditions. So, you know, that kind of mechanical hardening is a big one. Another one on this is, you know, there is some more kind of, you can go into more detail with these, as a lot of these, as far as just reliability of equipment, best practices for, you know, different types of electronics that are, you know, reliable in different environments and scenarios, you know, whether it's a radio itself, whether it's a power supply, you know, making sure that that equipment isn't going to become the weak link in your station.
All right. Well, I think that's about it for this evening, Jeremy.
I see.
Might be a few in here still.
Yep, I think I see two more, and I can grab them if you don't see them, Alex. The first one says, what about hardwired surge protectors that go into bus bars instead of in between mains and the main breaker? So that in they may exist. The hardwire surge protectors I've seen are designed to use the ground bus that's inside the panel. And in an NEC compliant, which means commercial, installation of a distribution panel, that the ground bus bar inside the distribution panel is bonded to the main bus bar, and you know, that's bonded to you know, whether it's a grounding ring, building steel, you know, that's all grounded together, and that is, you know, sized appropriately to handle any surge. So the not necessarily then a need to directly bond that to a bar, because it's bonded inside the panel, which should be designed sufficiently. And then, okay. Alex, did you make sure?
I think there was another one looking for a model number. Yeah, I did. So if anyone is still looking for the link to the slides, they're in the chat. That should have gone out to everyone. That's a Google Drive download link for the PDF.
And also, if anyone is having trouble seeing that, they can send me an email, which is my call sign, KB1REQ@gmail.com. And I can send you the link directly there if there's any issues with Zoom. As I know, it can be finicky sometimes. So if there's any issue getting it from the Zoom chat, definitely welcome to send me an email. Also welcome to send me an email with any questions that kind of arose from this that you want to cover. And I am stalling to get the model number. So the model number for the that plugin, that little plugin that that I reference there is the Transtector SL Sierra Lima 120. That's their version. Triplite also makes a version of it that I'd have to look up the model number on that. But that's a fairly common device. And like I said, I like that because it's easy to bring with you. And I have that on a lot of the repeaters that I've deployed with my clubs, just because it's a, an easy solution for that. So SL120 should get you more information on the Transtector version of that. Okay. Yeah, so Alex, I see you resent that, so thank you. And
Yep.
again, if that's still an issue, feel free to reach out directly via email. And I think that covers all of our questions. Thank you everyone for joining tonight. I appreciate your time and I appreciate the great questions. So everyone take care, and look forward to people joining us on our the rest of our sessions here for Ares Academy 2020. Thank you everyone. Have a great night.